Thank you for coming back for the second lecture of Thomas Vidick, and so on surprises in quantum complexity theory.
Hey, thanks, Michel, and thanks everyone for coming back. So today I'm going to zoom in a little bit and give some ideas that go into the proof of one of the results that was mentioned yesterday. I won't be able to do like even a comprehensive proof sketch or anything. So the way I structured the talk is in three parts. I'll say what the three parts are. The parts are loosely connected. You won't be able to get all the logic, but hopefully they will make sense. And my goal is to go from a general result and arrive by the end of the talk at a very specific question that is the heart of the matter. So the question will be a question that has to do with groups and stability. But before I get there, so let me remind you of the setup. So I'll state what is the theorem that we want to prove. So our goal is to show undecidability result. So we will do this by reduction from a problem that we know is undecidable. So that's the halting problem. And Turing showed that the halting problem is undecidable. So the halting problem you're given as input. So this is our goal. Tell me if I should write much bigger. Right? If I write too small, someone at the back will stop me. So the goal is to transform an input to the halting problem, which is just a Turing machine. So this M is a Turing machine. I'll abbreviate it often as TM. If you don't know what Turing machines are, it's okay. Think of it as a piece of code. An algorithm could be code in Python, in C, whatever. And the question in the halting problem is, suppose that I execute this code, is it going to halt or not? Okay, and that's an undecidable problem. We want to show that another problem is undecidable, so we're going to show it by reduction, transforming instances of the halting problem into instances of our problem. Okay, so what's our problem? It's this problem about quantum correlations that I discussed yesterday, so I'll remind you of the setup. So an instance of the correlation problem is specified by, first of all, we have a finite universe. This is the set of observations, okay, call it finite universe. It's the set of observations that can be made. Then we have a collection, curly S, of subsets of the universe of bounded size. So you can think of T as being equal to 3, let's say. These, I called them contexts. Okay. So a context is just a set of variables. And for every context, for every S in S, curly S, whatever, curly S, I have a constraint on the variables that are in this context. And the constraint is just expressed by a function phi sub S. And I think of it as a subset of assignments to the variables in the context. Okay? So this specifies which outcomes are accepted or valid for that context. And so we want to transform Turing machines into this kind of data such that two things hold. First of all, if the Turing machine halts, then it should be that the system of constraints that's specified by this data is quantumly satisfiable. And I'll remind you what this means, but just to write it on the board, it just means that the value of this system of constraints, I just denoted phi, would be 1. Okay, I'll give the definition of that in a sec. And if the Turing machine does not halt, then this value is not 1, bounded away from 1, arbitrary. Just arbitrary. I'll choose half here. Okay, so as soon as you've managed to do that, and as long as the reduction is efficient, so you can efficiently compute this data given the description of the Turing machine or given your piece of code, then you've shown that the problem of deciding between these two values or this problem is undecidable. Okay, which is our goal. So I just take this as the starting point. Yesterday we saw some motivation for this question, but today I just want to solve it. Okay, so I need to define what is this quantum value. So omega star of phi is the supremum of some other quantity, phi A. A is what? A is an assignment. So supremum over all A, quantum assignment. Assignment to the variables in my universe. All right, so what's a quantum assignment? So a quantum assignment is specified by a collection of observables. So first of all, it's specified by some integer, d, which is my dimension parameter, and then a matrix, OU, so finite dimensional complex matrix for every u in the universe that satisfies certain constraints. Okay, I want this to be a non-commutative generalization of plus minus 1 assignments to the elements of my universe. So I will realize that by requiring that these things are self-adjoint. So the star is just the conjugate transpose here. Complex numbers are not important. So if someone doesn't like complex numbers, you can just have everything be real, and this would be a transpose. And they square to identity. Okay, so then they have real spectrum, and the spectrum is just plus minus 1. Furthermore, we have a commutation condition, which is that whenever I have a context that appears in my system of constraints here, and I take two variables that lie in the same context, then the associated observables should commute. So OU prime equals OU prime OU. So this is a quantum assignment. And given a quantum assignment, I need to tell you what value it gives in my system of constraints. So what's the probability that this assignment satisfies the family of constraints. And so there's two steps. So first of all, given an assignment A, I can define a family of distributions P of A sub S given S. So this is an element of plus minus 1 to the S. S here is one of my contexts, so it's just a collection of three variables, let's say. I can define a distribution on this set as follows by taking, this is a formula that we saw last time, 1 over D, the trace of the product for U in S of 1 plus AU OU by 2. This is maybe the most intimidating formula that will be in the entire talk, so I hope that you can parse it. The way to think about it is that this context S specifies three different variables. By this condition, I know that the three observables, the three matrices associated to these three variables pairwise commute. Because they pairwise commute, they admit a simultaneous eigendecomposition, and so the entire space can be partitioned into eigenspaces, simultaneous eigenspaces of the three matrices. And the probability of a triple here, let's say 1, 1, 1, is just the relative dimension of the joint eigenspace of the three OU matrices associated with eigenvalues 1, 1, 1 for each of them. Okay? So this distribution is just like taking, this trace is just measuring relative dimensions of eigenspaces. Yeah. Yeah, yeah. That satisfies these conditions. Yeah. It's also part of the conditions. Yeah, yeah. So an assignment is an integer D, and so U is finite, so a finite collection of observables that satisfy these constraints. And yeah, the way I gave it here, yeah, yeah, because this last condition depends on it. In particular, if you take very large curly S's, you will have assignments that so that all the matrices commute, and that's something we generally want to avoid. So this curly set will not be all subsets of size T, but it will be a relatively small collection of subsets. And so given an assignment, I can associate a value to it in my constraint system. So if I have a constraint system phi and an assignment to that constraint system phi, I can define this value, which is just the expected probability that it satisfies the constraints. I'm sorry, I forgot over there that there should be a distribution. So pi, a distribution on curly S. Usually I will take pi to be the uniform distribution. We will not worry too much about it. So I just take a random context or constraint according to that distribution, and I sum over all possible outcomes S. And then I will count the probability that the outcomes satisfy the constraint. Okay, this is 1 if the outcomes satisfy the constraint, and here I will write the probability of obtaining these outcomes under the assignment A. Okay, so this distribution depends on A. All right? Yeah.
Sigma is the plus minus one. This matches exactly what you expected. A and B agree.
Here? Yeah, right. So maybe I should say that. So if so, a special case of all this is the case where D is equal to 1. In this case, these OUs are just plus minus 1 values. And this here is just equal to 1 if A is equal to these plus minus 1 values and 0 otherwise. So it's a deterministic distribution that just is equal to 1 at a single tuple A sub S. Okay, and this would just be the fraction under distribution pi of constraints phi s that the assignment satisfies. Okay, just for larger D, we have these matrix assignments that basically are a way of specifying distributions on assignments locally. Okay. What is what? Sorry. Did I have it now? Yeah. Okay. So phi s is a subset, and so phi s of A is just the indicator of the subset. So maybe I can write it here. Yeah, sure. Yeah, that's fine. Yeah. Yeah. Sure. So I just compute the total probability of the satisfying assignments. Okay. Yesterday we saw an example of such a constraint system, the magic square, where the size of U was 9. There were 6 different contexts, and the constraints were linear constraints, so constraints on the product of the outcomes in each context. Okay. And this was an example of a system of constraints such that this value here was 1, but if I restrict the dimension to being 1, then the value was less than 1. Okay, it was 5 by 6. Other questions on the formalism? So I've completely specified what we're trying to do. And we're going to achieve it using a general method to show that the problem is undecidable. So this method is called compression. It's going to involve mapping instances of our problem, so here systems of constraints, to smaller instances while preserving or even increasing their complexity. So this will be, let me say what the 3 parts of the talk will be. So part A, I want to talk about this general method, compression. So I'll state a general result and explain a little bit how we apply it here. Part B, once we understood, this will tell us what needs to be done. Once we understood what needs to be done, I'll talk about PCPs, so probabilistically checkable proofs. This will be very short. It will just be a way to transition to the place where I want to arrive at, which is questions about stability, which are the sort of technical heart of what we're trying to do. All right, so let's talk about compression. I will formulate this generally, so you can put aside this. Maybe I'll try not to touch the 2 boards on the left, and just focus on this here. So what's the setup? So my setup, I need to be given the following things. First of all, a language. What's a language? It's just a subset of all bit strings. So for example, this could be all bit strings that represent a Turing machine or a program that halts, okay? Or it could be all bit strings that represent, using some kind of encoding, a system of constraints, or okay, something like this. I also need to be given a function, f. This function maps strings to integers, possibly infinite, okay? But it needs to be finite on the language. So for every x in L, f of x is finite. Okay, and the last thing is I need to be given is a compression function. Compression function. Okay, to state what this. Okay. To state what this should achieve, I need to tell you about a little bit about something called implicit or succinct representations. So here's another definition. A pair of E and N. Okay, so what's E? E is a Turing machine, so it's an algorithm, it's a program. So this is a Turing machine. N is an integer. And I want to define what it means for this program and this integer to succinctly represent a very large string. So is a succinct representation of some string x, okay, if the following conditions hold. First of all, x should not be too long, okay, but it can be pretty long compared to the integer n, but not too long. And E, as a program, computes the elements of x. So for every integer m, E of m is equal to x of m if m is less than the length of x, and 2 otherwise. Okay, 2 is just a value that x cannot take, so it's just to say that we run the program on an integer that goes beyond the length of x. It's going to tell us, you're out, so 2. All right? Yeah. Yeah. So usually this maybe more standard would be to write it like this. Yeah. Okay. So think of the string x is very long, but it has a little bit of structure. So not every string is going to have a succinct representation. But if this string has a bit of structure, for example, x is the string 0, 1, 0, 1, 0, 1, 0, 1, of a certain length, then there is a short program that computes the mth digit just by checking if m is even or not, and maybe checking if m is too long. Okay, so some strings have succinct representations and some don't. Okay. So now I can state a general theorem. I'll call it a lemma because they call it a lemma. So this is due to Marx. Nezadi and UN. It's a result in logic. Okay, and it states that under some general conditions, the language L will be uncomputable. And so there will be a reduction from the halting problem to L if the following conditions are satisfied. So suppose that there exists, and here I will write polynomial time. So function or algorithm, and this is important, called comp for compression. Okay, and this takes as input succinct representations. So succinct representations are just pairs of an algorithm and an integer, and it maps them to explicit representations, so just strings. So it takes as input, I will write it as x hat, and it maps it to y. Okay, when I put a hat, it means succinct representation. So x hat is a pair of an algorithm and an integer that succinctly represents some x. So you put in my compression such that this, such that two conditions hold. First of all, f. So remember we had a function f here. This f should increase through compression, okay, by at least 1. And second, this compression function should preserve membership in the language L. So x in L implies y in L. Okay? So suppose that all these things hold, then the halting problem reduces to the language L. Okay? So yeah. Right. Yeah. Yeah. Did I not? Yeah. Sorry, I didn't write it over there. Yeah. So I'm just representing the Turing machine in some arbitrary manner. I will list the states and the transition function. So yeah, that's E. So this X is like some E and yeah. F is here. So F is a function that was given ahead of time. It's a function that need not be computable. And it's a way to think about it is that it allows me to certify that an element is not in the language. But the only condition on it is that it's defined everywhere. And on the language, it's finite. Outside, it could be infinite or it could be finite. So this function could be just the zero function, for example. But then I will never prove this theorem, right? Because it needs to increase through compression. Well, I mean, this is how x and y are defined. So I should have read here such that for any, here is that for any succinct representation of x, of some x, and if I let y to be the compression, sorry, x hat n to be the compression of x hat n, then these conditions hold. Yeah. Okay, other questions on this? So, yeah?
Does this definition imply the compression is shorter than x hat n? Or do you need to have it disappear?
No, it doesn't. The only thing is that it should, no, it doesn't. It's generally going to, so y is generally going to be longer than x hat. It's going to be polynomially longer because this runs in polynomial time. So it matters that y is not too much bigger than x hat. And that's it. Then the way I define exactly my succinct representations is up to me. I mean, it's just up there. So maybe I will tell you in a second how maybe let me tell you now how this is applied. So I will. I don't think we need to keep the board on the left, so I will just cycle through the boards. Yep.
First argument to compress as a Turing machine, right?
Mm-hmm.
So I'm getting succinct representation of x
Yep.
and the natural number.
What's what?
What is y signified?
Why is the compressed version? So maybe I will give you an example. We will apply it to this problem. So you have to, I mean, one way to think about it would be if you think of a constraint satisfaction problem, an explicit representation of it would be circuits that compute the constraints, and a succinct representation would be a Turing machine that computes specific gates of the circuit. And so in your head, you have to think of a succinct representation as a way to represent in total size n, or if you want, like, log n, to represent something that, let's say size n, to represent in size n something that has size exponential in n. Y has size n, and it's a system of constraints that has size n because it's an explicit representation. I will tell you how this is applied. Maybe it will make it a little bit more concrete. So,
In that lemma, you have an x and L. And
yeah.
Is x the same as e?
No, x is the, so x is the succinct x hat is a succinct representation of x. It's here.
Oh, okay.
So these conditions should hold whenever I have a valid succinct representation of an integer, not an integer, whenever I have a valid succinct representation of a string x, and y is a string obtained by compressing this succinct representation, then these conditions should hold. X and y are strings that are related by the compression function.
X hat, comma, n, is that the same? I mean, x hat was e, comma, n.
Yeah, I'm sorry. Yeah. So e comma n is x hat. Yeah. So let me tell you how this is applied here, and I will say what these representations are. So in this case, so the language, this is simple. So it's the set of, I erased it, but the set of constraint satisfaction problems phi, such that their quantum value is equal to 1. Okay, so satisfiable systems of constraints. The function f will be such that f of, so now instances, instead of writing them x, I call them phi. So f of x, f of phi will be the smallest d, so infimum of all d in n, such that there is phi a is bigger than half for some assignment a of dimension D. F is a measure of the complexity of an instance of the problem. And here I just define it as the smallest integer d, such that there are matrices of size d by d, such that when I evaluate the constraints on the distribution implied by this collection of matrices, I get probability bigger than half. Okay? So if I take an instance in the language, there is a collect by definition of what this means. This was defined as a supremum. So there will be sequences in increasing dimensions of matrices that achieve values arbitrarily close to 1. In particular, for value half or 3/4 or 9/10 or whatever, there will exist matrices of finite dimension that achieve this value. And so the condition that the function f is finite on the language is satisfied. Okay, and how will I represent my systems of constraints? I will represent them using Turing machines. So an explicit representation, I have to decide, I defined it in like mathematically, abstractly, but I didn't say how these things are represented just as strings. So an explicit representation of phi, this will be given by a pair d and an integer n in unary, such that d computes the constraints. So here I'm being a little bit informal. So such that d is a Turing machine, d is a Turing machine such that if I give it as input a set S and an assignment A, it computes whether A is in phi sub S. Okay, and it runs in time at most n, and runs in time at most n. Okay, and a succinct representation will be the same, except that it will write n in binary. So d n such that the same. Okay, so you can verify that these are valid. This is a valid succinct representation. These are valid succinct representations of these. And this means that the goal, in this way of representing things, the goal of the compression function is to take as input a system of constraints that's specified, it's taking as input succinct representation. So a system of constraints that's specified by a Turing machine. So you have an algorithm that verifies the constraints, and it runs in time here, so it runs in time n, and here it's going to run in time 2 to the n. So, such that, etc., and runs in time. Sorry, I think I did it the wrong way around. Yeah, it's the other way, sorry. So n and 1n, and they run in time polynomial in this input. So here it runs in time polynomial in log n, the length of the description, polynomial in log n, and here it runs in time polynomial in n. All right. It's no, so here, right, so here so the one thing that I stated precisely is the compression lemma. How it's exactly applied, I'm not saying this very precisely. So in particular, yes, when I write phi, I mean the entire description of phi. So here my succinct description is not complete. So a complete succinct description would have to also have algorithms that specify what the universe is, what the contexts are, and how to evaluate the constraints.
So the original phi was a collection of subsets of
What I mean by phi, in what I write. No, it's a specific instance. So what I mean by phi here is a specific universe. So phi, I mean the collection of all these objects. So a specific universe, a collection of contexts, that's a subsets of the universe, and a collection of functions of subsets phi s for every s in curly s. Okay? So a system of constraints, a fixed system of constraints, is specified by all this data. The universe, the contexts, and the constraints for each context. Okay? So these are the objects that we're talking about. So I need to say how these things are represented as bit strings. Okay? And the way I say that they're represented in bit strings, this is what I call explicit representations. Actually, what the bits, you could choose many different representations. I could choose to, like, for example, my string could be, I don't know, first interpreted as a list, as an integer that represents the number of elements of the universe, and then some other integers that represent subsets or whatever. That could be a way to do it. This is not the way I choose. The way I choose to do it is that this bit string is going to specify some algorithms. And these algorithms are algorithms that I can run. And when I run them, they will label the elements of the universe, they will label the contexts, and they will allow me to evaluate these functions. Okay? And then depending on the runtime that I allow for these algorithms, this is how I distinguish in this specific application between explicit and succinct representations. So succinct representations are allowed in this representation more time, so they can represent in the end universes that are bigger, contexts that are also larger, and constraints that are maybe more complex to evaluate. And like loosely speaking, the goal of designing the compression function is to start with an instance, so a phi that is large because it's computed by an algorithm that runs in a larger time. And I want to squish it. I want to find another system of constraints that can be represented explicitly in the same amount, in the same size. So it means that it's a system of constraints that is smaller, but has the same properties. So if my system of constraints was satisfiable, the new system of constraints is satisfiable, etc. Okay, so yeah. A particular what? Well, I gave you the f here. This is the f that I'll use. Yeah, so it's, this is, yeah. It's not, I will not, now I will make a jump. I will make a couple jumps. I will not apply this directly, so it's not extremely important that you understand the application. What I wanted is to state the general theorem to give an idea of what's the strategy that we're applying. Yeah. Instead of what?
Like you've written here that this, like again, the definition.
Yeah.
You run the Turing machine for m steps.
Yeah.
So m is the second argument.
Yeah.
But in that case, like those two things you've written would be the same.
Sure. Yeah. No. Yeah. So you're right. So this is not exact. Yeah. This is not exact. So yeah. Sure. Yeah. Yeah. The definition here is correct. The way it's applied, I wasn't exact. It would take too much time to be exact there. So it's not. Okay, I'll continue. I mean, the high, Turing machines and everything, the details about these are important, but it's not, like for the level at which I want the talk to be, it's not so important. The flavor that I wanted you to have from this first part is that in order to show that a certain computational problem is undecidable, it's going to be sufficient to transform instance of the problem to smaller instances, so instances to smaller instances such that you maintain membership in the language. I didn't show the proof of I'm not showing the proof of this lemma. It's not hard, but it's some arguments in manipulation of Turing machines. So you use clean recursion theorem. You have to feed Turing machines to Turing machines. So there's a little bit of a fixed point argument there that I want to completely skip. Now I want to just give you an idea of how we manage to do such compression of the systems of constraints that we're studying in a very simple case. So let's consider the following. Okay, so this is part B. So let's consider the following situation. So I have a universe. Okay, and I'll simplify a little bit. I'll just label my universe using integers from 1 to n. I have a certain set curly S of contexts on that universe, and I will consider only linear constraints. So I will imagine that for every S in curly S, I have a plus minus 1 value beta S. And this beta S specifies a constraint phi S. So phi S is the collection of all A in plus minus 1 S such that their parity is this value. Okay, so product for U in S of AU equals beta S. Okay, so this is a system of linear constraints. I have a certain number of subsets, and for each subset, I have kind of a right-hand side for my linear constraint that says, okay, this is no. So it's a parity constraint, and our goal is to, based on what we said earlier, our goal would be to compress this system of equations. So I would want to find a smaller system of equations, so that has fewer variables, fewer contexts, maybe smaller contexts, but that preserves satisfiability, such that if the original problem was satisfiable, then the new problem will be satisfiable as well. Yeah?
Maybe you mentioned this, but why was it important that the compressed was polytechnique mutable? Because you're going to apply this at the level of like...
Yeah, it's very important in the proof, but basically here it guarantees that the size of y as a string is not much bigger than the size of x hat. And this is why I think of y as a compressed or smaller representation, because the size of x hat, this can be exponentially smaller than the size of x itself, right? X can be a string of length 2 to the n. X hat can be a program of size roughly n. So y now is a string of length also roughly n, or n squared if this machine is, okay? So this is why it matters. If I allow it to be, let's say, exponential time, then the theorem is false, because the compression function could just undo the succinct representation, and it could just return basically x itself. Okay, but that cannot be done in polynomial time in general. And so. Okay, so our goal is to you have to be a little bit like, if you think of this as just a system of linear constraints that you're trying to solve. Classically, meaning for dimension 1, you can solve this, and so you can do everything. But I also told you, mentioned yesterday that the question of, even for linear constraints, the question if phi is equal to 1 or not, this is an undecidable problem. Okay, so it's not so easy to manipulate systems of constraints even like this. And because I want to get to the last part, I'm really going to skip like a million steps here. I will just show you how we would go about reducing not the universe size, which is the key point, reducing the number of variables, but instead just reducing the size of the contexts. Okay, so it's a very mild form of compression, but it'll allow me to introduce the next part. Okay, so please allow me to do that. So here is the transformation, the sort of like I don't know, a simplified compression that we'll do here. So we're going to, in fact, extend the universe, and we're going to get a much bigger universe, U prime. U prime will be the collection of all subsets of the integer 1 to n. Okay, so I represent them as n-bit strings in this way. And my idea, what I want to try to achieve is that if, let me use colors, if we had an assignment to this problem, so it's just a collection of D by D matrices, OU, right? An assignment to the problem here that I haven't defined yet, I'm going to define it in a second. I want it to be, well, now I need an observable for each possible n-bit string, so I will denote them by O sub s, and I would like O prime sub s. I would like O prime sub s to be the product for u in S of OU, okay? So I greatly extended the universe, but what this will allow me to achieve is to reduce the size of the contexts, except that it's a worthwhile goal. And my idea to do that is to start from these variables and instead define new variables that are obtained by taking products of the old ones across any subset, okay? So this is how I changed the universe. Now I need to tell you what the set curly S is. So curly S will be mapped to curly S prime, which will have two components. First of all, so for each element of curly S, I can now represent it as a single element here, S, for every S in curly S, okay? This is because when earlier I wanted to check a linear constraint on a subset S of variables, now this subset S of variables corresponds to a single new variable in this new universe, which is just a variable that's indicated by the corresponding subset. And so my linear equation just becomes whether a specific variable, just one variable, is equal to beta S. Okay, so the phi, maybe I will write the betas here, so beta prime. The associated beta will just be here, in this case, the beta S. Okay. Now, if I do just that, this is never going to work. This new system of constraints is always going to be satisfiable because I can just, I don't need to have O prime my variables to satisfy this kind of condition. I can just define new variables, and these new variables could just be equal. Whenever there's a constraint, they would just be equal to whatever the right-hand side should be. And whenever there's not a constraint for a certain set in my new universe, then I put whatever I want. Okay, so we need to add some additional constraints that will check that any assignment, any satisfying assignment to this new system of constraints will have this form. Okay, and so the natural constraint to add are some linearity constraints. So I will just add here S, T, and S plus T. So the sum modulo 2. For every subset ST of 0, 1, n. And the associated beta will just be beta ST S plus T equal to 1. Okay? What this means is that I'm adding a constraint for any three variables that are indexed by sets S, T, and their symmetric difference, S plus T. I add the constraint that the product of these three variables should be 1, okay? Which is the case if my variables have this form, okay? If O prime S is this, I take the product of this times with a set T and then times with a set S plus T, everything will cancel out. So, I mean, I'm using a little bit succinct notations here, so I would say like, I need to specify some beta prime S prime for every S prime in S prime. I need to specify what it is, okay? And I'm just writing if my element of S prime was this singleton, then I copy the old variable. If it was this triple, it's just 1, and that's it, okay? So what this has achieved is that it has greatly increased my universe, which is absolutely the opposite of what I want to do. I want it to reduce. But it has at least reduced the size of the contexts. Before, my context could have any size t. Now t has disappeared, and they have size at most 3. Okay. Now I want to write here what is needed in order to analyze this. So what you would like to show is that any assignment to the variables of the new system of constraints, because of these constraints that I added over there, has the form that's written in blue in the board. If it has the form that's written in blue on the board, then I know that I've simulated the original system of constraints correctly. So what we would like is to have the following statement. So what we want is, well, what we want is that we'd like to show that suppose that some assignment A prime is such that this assignment is a good assignment for the compressed system of equations. So let's say that this value is large. So I mean, what I want is like this is a half. Then there exists some assignment such that phi A is also bigger than a half. Okay, I want to relate the value of these two things. I will not in general obtain something like this, so you need to play a little bit with the values, and I will want something a little bit weaker, which is that if this is close to 1, then this is also close to 1, and there's some function of epsilon here. Okay. In order to show that, it's sufficient to have the following. So we would like the following. So suppose that I have so this A prime is just specified by a collection of observables OS, where S ranges over all elements of 0, 1 to the n. So suppose that this satisfies my constraints over there, and I'll focus on the constraints that I added, the linearity constraints. So what does it mean to satisfy the linearity constraints? It means that these observables will multiply correctly like this. So suppose that OS are such that the following holds. So when I take two random subsets S and T, and I look at the product OS, OT, OS plus T, this is close to the identity. Okay, and I will need to measure this using a certain norm. I will tell you what the norm is in a second. So suppose that this is, okay? So this is a condition that expresses, suppose that my assignment satisfies the constraints over there, so I search at this. Then, and I want primes here, then there exists some OU, U in 1 up to n, such that on average over S, O prime is equal to the product for U in S of OU. And then here I would have a delta of epsilon. Okay? So this statement says that suppose that I have a large collection of observables that satisfy these linearity constraints as expressed by this equation, then there exists a smaller number of observables that explain the linear observables in the sense that minus, yeah, sorry, thank you, such that this. All right. So let me tell you what the norm is and specialize to the dimension 1 case. Yeah, so that's what I was going to say. Yeah, exactly. So, but I just didn't assume that everyone knows BLR. So I guess Onit was here or is here. Yeah, Onit is here. So maybe first let me tell you what the norm is. So this norm is just the appropriate norm in this setting is the Hilbert-Schmidt norm normalized by the dimension. Okay. So this is the norm that you get just based on the way that I had defined probabilities earlier. So if d equals 1, this is a theorem. So if you take d equals 1, you're given 2 to the n values such that these values satisfy approximate linearity conditions, and you can show that in that case, these values come from a linear function. So maybe I will, yeah, if d is equal to 1, this is the Bloom-Luby-Rubenfeld theorem. Okay. So what I mean by if d equals 1, I mean if these observables are dimension 1 observables. Okay. In general, D it's also a theorem that's due to myself and Ito from like 10 years ago, and the proof is very similar to that theorem. It basically uses Fourier analysis, and yeah, I'm low on time, so what I want to do though is go to the third part and formulate this question. So as a more general question. So let me go there. I will take a few minutes to ask a general question about groups, and then I will connect that question. I will go back to this statement and argue that this statement is a special case of my general question. So the general question is as follows. So take a finitely presented group, and I will give an example soon. So G equals SR, a finitely presented group. Okay, what this means is that S is a set of generators, finite set of generators, and R is a finite set of relations. Let me give you two relevant examples. So I will take a very simple group. I will take the group Z2 to the n, okay, as a group, with addition modulo 2, and I can give you two different ways of presenting that group. So one is what I would call the exhaustive presentation. Because it's a finite group, I will just list all the elements of the group. So I can have as generators elements E sub S for S an n-bit string. Okay, so this is just, there's 2 to the n generators. We just index the possible elements of this. And the relations are that these elements should square to themselves. Okay, because we're doing things mod 2, and they should multiply the way that addition mod 2 works here. So I should have ES ET equals ES plus T, okay, for every ST. All right. So this is a presentation of the group Z2 to the n that just amounts to listing its multiplication table. Okay, all the elements of the group and all the relations that these elements satisfy. Sorry, which one?
I don't understand why you're including ES squared.
Because it's included here?
No, it doesn't seem to be.
Sorry. Equals the identity. Yeah. So the identity will just be equals 1. Sorry. Yeah. I can write down a more succinct presentation, which maybe is more natural. Then I will just include generators E1 up to En. Okay, that's it. Only n of them, and I will have also the condition that EI squared equals to 1. So they're idempotent, and they commute. So EI EJ equals EJ EI for every I nj. Okay. This is the same. You can generate Z2 to the n by taking n commuting involutions. Okay, so it's the exact same group, but this is a much more succinct way of presenting the group. Okay. Now I will define a notion of approximate representation of a group. So definition, a certain function f from S to unitaries in dimension D is a epsilon approximate representation of a certain presentation, so of G equals S R, if it approximately satisfies the relation. So if when I take a relation at random, okay, and I evaluate the function on the relation, I get the identity f squared less than epsilon. So there's a few things that are underspecified here. First of all, implicitly here, there's a distribution on relations, which I didn't say what it is. So as part of the definition, this would be epsilon approximate representation with respect to some distribution, but let's just imagine that the distribution is uniform. There's a finite set of relations. And what do I mean by that? Okay, well, if the relation is of the form ABC equals 1, the relation are just like words like this in the generators. By this, I just mean f of A, f of B, f of C, okay? The function f only maps generators to matrices. This is the same norm as earlier. And so this is saying that the function approximately satisfies the relations. In particular, if I set epsilon to 0, then this is just a representation. Okay. And now another definition will be that the presentation G equals SR is stable. So there will be a parameter delta stable if for every epsilon approximate representation F, there is a representation G, so an exact representation G that goes from the generators to matrices such that the two of them are close. So I need again a distribution, this time a distribution on generators, f of s minus g of s delta. So delta can depend on epsilon. Okay, so for every epsilon, every approximate representation is such that close to it there is an exact representation. Okay, so something that exactly satisfies the relations and on the generators is close to the approximate representation. Are these definitions okay? These two definitions? Okay, so I'm a little bit out of time. I'll maybe just take like 4 extra minutes or 2 extra minutes. Is it okay? So just to talk. So
delta stability also implicitly depends on the primitive.
On what?
So
Delta can be a function of epsilon. Can be a function of epsilon. So in general, you would want delta to be, the best possible function. You can define now for a presentation, it's modulus of stability as the best possible delta, okay, as the best possible function delta. And let me just, to conclude, say just a couple small things. So here, now this question is exactly a question about stability of the large representation that I had over there, right? If you take the representation that's on the top board, the first one, this has generators, I chose as generators all the elements of the group, and as relation, the multiplication table of the group. An approximate representation for that presentation is exactly something that satisfies, that gives me a matrix O, so this O is f of s for each of my generators, and it should approximately satisfy the group multiplication relation. And this condition is exactly that it's close to a representation because these O's here, these are exactly a representation of the group. So what we needed, so I will just write it like this. So what we needed is that this presentation z to n equals ES. I'll write it a little bit succinctly here. It's the same as over there. Equals S plus T is some function of epsilon stable. Okay, and this is true. And in fact, every finite group, for every finite group, the presentation of it that just lists all the elements of the group and the multiplication table is stable. It's a result of Gowers and Hatami, and in fact, it's true for some infinite groups, in particular amenable groups. I mean, they're infinite groups, so you have to adapt a little bit my definitions with averages, but you can do averages on amenable groups, and they are also stable. Okay, yeah, that's the key point. Yeah. So for example, so now the place where things get interesting is that this is not good enough for us. I talked about, we arrived at this particular presentation because of the way that I did my compression here. And I highlighted when I was doing it that this was not so good because it blew up the size of the universe. Okay? So it turns out that if you want to do this truly efficiently, you need the key element that you need is presentations of Z2 to the n, the same group, that are short and yet remain stable. Okay. So you can try this on the short one. We have a short one over there. Unfortunately, this one, so Z2 to the n equals just the generators and these relations, so EI, EJ equals EJ, EI. This is stable, but it depends on n, so n epsilon stable. Okay. And this n is natural if you think about it, because a representation is something that needs to be defined on the entire group. And here, because I chose so few generators, my approximate representation is defined only on n generators. And the size of the group is 2 to the n. So to study how the function behaves on the entire group, I will need to take products of n generators. And if the relations on these n generators were satisfied to error epsilon, when I start taking products of n of them, I will get error n epsilon. And so it's natural to expect this kind of a result. But it's tight. And so the main technical result in the compression argument, the way that we need to employ it is to identify a presentation of d2 to the n that is stable with that kind of stability. So it doesn't actually not depend on n in our case, but the dependence on n it's mild. It's like log or something like this. But that has size that's more of that order. So this has size 2 to the n, this has size n, and we want something that has size polynomial in n. And that presentation is obtained by from error correcting codes. But I will not really have time to discuss that more because I'm already too much over time. But that's the main thing that I wanted to, the main connection that I wanted to make. That in order to compress our systems of constraints, we're led to studying the stability phenomenon, and in particular finding presentations of certain groups, in particular the group C2 to the n that are short. This is what will lead us compression, and yet are still stable. This is what will allow our argument to preserve the satisfiability of the problem. And I'm sorry for being over time, so I'll stop here.
Any questions?
Stable.
So you need these stable presentations for arbitrary groups, or
no? So we need it for. It's almost enough. It's essentially enough to get it for that. So you can study. So this, I believe, is an interesting question in group theory in general, to study what kind of groups.
Yes.
The group can be large. You want a presentation. So there are very large groups that have very small presentations. You can have an infinite size group that has a presentation of size like 5 or something. So these are unlikely to be stable in the sense that I want. But anyways, it's an interesting question in general. But no, for our result, we only need it for Z2 to the n. You need it for something a bit bigger. But if you have it for Z2 to the n, you can extend to that bigger thing. So.
Any other questions?
Can you say anything about why you start with this compression problem? Like, intuitively, why would you try and? I mean, there's lots of undecidable problems, but.
So what's the question? So maybe at this. So do you accept that my starting point? My starting point was I wanted to show that a specific problem is undecidable, and this you accept. And then I went for a particular strategy, which is to design a compression function on instances of that problem, because I knew that this strategy would work. That was a way to show that it's undecidable. And you're asking why did I choose that strategy? Yeah. So it's nice. So actually, you can show that under very mild restrictions, any problem that's undecidable can be shown by compression. So there always exists, if a problem is undecidable, there will exist a compression function. So in a way, it's without loss of generality. Why did I do that in the first place? I mean, that's a different answer to your question. And it's just because we didn't start off by trying to show that a certain problem is undecidable. Usually you don't start from that. You start by trying to show that it's hard. So we first showed that the problem is NP hard, and then we show it's harder. So you shoot for NX or something, and this is things that Anand, who's here, Natarayan, did. And then you try to make it harder and harder. And a way to make a problem just a bit harder, it's rather intuitive that you would do that by compression, because the hardness of a problem is always a function of the input size. So saying that the problem is time t hard, it means that it will require time t of input size in order to solve it. Now, if you manage to take an instance and reduce its size while preserving membership in the problem, now if you already know that it's t hard, the reduced instance that has smaller size, this will take time t to solve. And then when you go back up, then you will have shown that it's like the time has increased by some factor, and you can sort of iterate that, and then there's just a fixed point argument there. But,
Thanks.
Any other questions? So then let's thank Thomas again.